For those of you that don't know me, my name is Stuart. I'm an assistant professor here at Portland State, and we focus on organic chemistry and developing new reactions for organic chemistry. And I'll discuss a little bit about that in my portion of the talk, and in the context of green chemistry. Following me, Dr. Tom Wilson will give a talk about their developments with green chemistry at Nike, and then Jim Tung will discuss some green chemistry concepts in his work in process chemistry with Lactalis Laboratories. But I guess at this point I should really answer the question, what is green chemistry, that was on all our advertisement flyers and emails and tweeting and what have you. So just to kind of start it off, green chemistry, and this was kind of defined by Anastas and Warner, is really thinking about chemistry and reducing or eliminating the use of hazardous substances. And so in that context, there's a lot of kind of synonymous with things like eco and sustainability and things of that nature. Okay? And so the other aspect of green chemistry, and the part where I really feel like there's a natural overlap with my own interests in synthetic chemistry, is that it's really an obligation that chemists as scientists have in designing safer chemical methodologies. And so when we design new reactions, we need to think about what we're putting in and what we're getting out of those. Okay, and so designing those to be safer, both to human health and the environment. Okay. So green chemistry is really kind of emphasized through these 12 principles. Now I'm not going to read them all out. Actually, for those of you that are interested, if you go to the ACS Green Chemistry Institute, you can get these little green chemistry pocket guides. You can always carry around the 12 principles of green chemistry. But what I want to emphasize is really some words that come up again and again, like prevention, safer, reducing, and really it's the concept that it's better to prevent waste than to treat it up after the fact. And this is really kind of something that has evolved in recent decades. That wasn't necessarily something that was a consideration for synthetic chemists, post World War II. And so, where does this shift come from in green chemistry? What has really forced synthetic chemists to think about designing safer methodologies? So, post World War II, synthetic organic chemistry had a lot of advances that brought you things like thalidomide and DDT. But there was also a public awareness that these had very, very detrimental effects on human health and the environment. And so that started to generate a culture of thinking about, we're able to generate these things, but we need to start worrying about what they do to humans and also the environment. And DDT in particular has had a detrimental impact on migratory birds and other animals. Additionally, waste was not something that was considered holistically. And so this molecule here, dioxin, is a contaminant, or one contaminant, in several really tragic stories. One being the Love Canal, which was actually a dump site in the 1940s for petrochemicals. And subsequently, when Niagara Falls was expanding as a community, several public schools were built on top of the dump site. And so ultimately, the chemicals leaching out had a terrible impact on the community. And Times Beach, Missouri, through the 1970s, dealt with a lot of the dust from their dirt roads by pouring gallons and gallons of oil over the dirt roads to keep the dust down. Dioxin was in the oil that was being used, and so ultimately was spread throughout the entire community. And again, it had terrible effects on the people and the animals and the environment at large. And so really thinking about all these types of organic compounds, what can we do to really create safer compounds? And these go back to several of the principles. Designing safer compounds, designing things for degradation. This is a useful insecticide, but it doesn't degrade. And so designing chemicals that would degrade and not have such a significant environmental impact. Principle number one, prevention. So instead of just dumping chemicals, preventing that waste so that we don't have to go back and clean it up through remediation processes. And again, design for degradation. Okay? And so, when did green chemistry start to evolve or emerge? And if you notice, a lot of those incidences that I had just discussed were through the 1940s and 50s and 60s and 70s. And so, this plot really just shows several years. And I would say that society got on board with being green before chemistry got on board with being green. And so, just as an example, the city of Portland established its first recycling system in 1987. So in the 80s, household recycling was becoming the norm. This plot shows publications with green chemistry in the title. Okay, so this is when green chemistry was really first conceptualized, and you can barely see it, but in 1991 there was one publication with green chemistry in the title. The title of that talk was Green Chemistry, Dream or Reality. So people were thinking about it. It was an idea, but it really hadn't come to fruition in 1991. In 1993, there was one publication with green chemistry in the title, and that was the slow birth of green chemistry. And so they were being patient. You know, green chemistry was on the way. Other people were thinking about it, but it hadn't really come full circle yet. There's a book, Green Chemistry Theory and Practice, that's published by, or that was written by Warner and Anastas, and Jim will have a few things to say about that book later. But that was actually published in 1998, and that really conceptualized green chemistry and brought it to the forefront of what synthetic chemists should be doing or should be thinking about when designing chemicals and methodologies for making chemicals. And then in 1999, the first issue of Green Chemistry, the journal, was published by the Royal Society of Chemistry, and that really allowed a venue for green chemistry to be published, and after that, you know, things really shot up. There was this dip here, which kind of resulted from green chemistry being rebranded as sustainable or eco. And also around 2004, 2005, green nano got on the scene, so that really shot everything up. And so now, in about 2014, there was almost 3,000 green chemistry articles published, with green chemistry in the title. So if anything, it's a way to get your work published, just put green chemistry. So I want to just move a little bit on from some history of green chemistry, give you a sense of some of the things that my group is thinking about. And to be totally honest, we're not green chemists. I mean, not in the sense that both Tom and Jim do green chemistry on a significant scale. So this is a round bottom flask, and for those of you that have done organic chemistry lab, this is a pretty standard piece of equipment. This holds 250 mils of a solvent, which is probably a pretty typical bench chemistry, at least in an academic sense, bench chemistry scale. You can load several grams into this flask, run a reaction, and that would be fine. Now, I don't want to discourage anyone, but the things that we tell you in Gen Chem and in sophomore, and things that you're learning in high school chemistry, for those of you high school students, they don't always really work when it comes to setting up a reaction. In fact, they rarely work. For organic chemistry student or organic chemistry graduate student, if more than a third of their reactions are working, they're probably not working on hard enough chemistry. Okay, just to give you a sense of we don't really know what's going on in here. We like to think that we do, but we don't really know. And so, in order to facilitate the discovery process, you know, it would be pretty wasteful for us to be using these on a regular basis. And so we actually use pretty small vials that hold about 3 mils or even less than 3 mils. Okay, so we dial things back a little bit. And we also use these blocks here where we can put the vials into these aluminum blocks and heat them, and so we can run lots of reactions at the same time and really take more shots at the basket, and hopefully we'll discover something. Now, the scale that we're doing things on is a real far cry from the scale that Jim's doing things on, and while we're working on milliliter scales, he's working on thousands of liter scales. So just to kind of give you an emphasis of the difference in the scale that we're working on, and of course these are obviously not to scale. If they were, my vial would be crushed by this thing. It's a little dot down there. So this is really the discovery stage. And not everything that we discover here works well here, and I'll let Jim maybe say some things about that. But this is actually one of the molecules that we've been interested in, that we've had some luck in discovering some new chemistry about. And for those of you that are in organic or Gen Chem, or I'm not sure where chemistry's at in high school these days, but this isn't something that we teach here. This is a triple bond, and the carbons are sp hybridized, and we teach you pretty emphatically that should be linear. Well, in fact, you can actually bend them. And when you bend them and constrain them in a ring like this, they're incredibly reactive. But that's a good thing. If we can generate these incredibly reactive intermediates in a programmed and predictable way, we can potentially do some really interesting chemistry with them. And so these intermediates have been used in several occasions to make natural products and drug-like molecules, because one of the things that they do, because they are so reactive at either end of this bent triple bond, that you can put two different substituents on that triple bond in each of these cases. And so you can build up some molecular complexity pretty quickly from kind of a common intermediate here. And so this is something that we've been really interested in doing, and I'll give you the full story. We arrived at this in a very serendipitous way. So in addition to having lots of little small vials and lots of blocks to run them in, the other thing that really helps the discovery process is having really talented graduate students. Okay, and so I would love to tell you that the discovery that we made was a well thought out hypothesis, but it actually wasn't. But it did take a lot of hard work and some keen observations made by a graduate student. So this is another molecule that we're interested in working with. And we work with some weird molecules, strained up triple bonds, and then iodine here has two bonds to it, and that's not common either, but it confers some high reactivity to the iodine center. It's positively charged, and so this thing is known to react with nucleophiles, or compounds that have electron density. So things with a negative charge want to come along and attack this iodine with a positive charge, and that's a known site of reactivity. And that's why we were interested in this molecule. We thought we could do some cool things with this and form some new bonds at this carbon by reacting at this iodine center. Okay, and so we had lots of little vials set up with reactions that we were testing. And what Sunil found was that in actuality, if he uses the right base, it attacks here. We break this carbon-hydrogen bond, we break this carbon-iodine bond, and we get this strained intermediate. And it started off with just a very small side reaction that he bothered to analyze that product, and that has led to a whole new research area for our group. So that's kind of the serendipitous side of things. But how does this relate to green chemistry? So if we wanted to make this strained intermediate here, we would use this compound here that Sunil can make. And the reason that this is a green approach to these Orion intermediates is that we can make these compounds in a single step. And this is just one example of how we make them. We have several routes to these compounds, but this is one example where we can take a commercially available boronic acid, we can take this commercially available compound, all of these things are commercial, and we can run this reaction. This one takes about 12 hours, but there are others that take less time, within an hour, and we can get this compound, okay? Now, competitively, the previous approach, and really this highlights that green chemistry is relative, okay? This is a new discovery, and so previously, the way to generate this compound required a precursor that took 3 steps to make. And so you'd have to start with this chlorophenol, carry out a reaction, isolate this, carry out another reaction, isolate this, and carry out a third reaction, which would take a total of about 48 hours, okay? Moreover, we can isolate this by simply filtering the solid product. And so the barrier for isolation is really low, okay? That doesn't require a lot of solvent. And we can take about 10 millimoles of this, which is about 1.5 grams, and get about 4.5 grams of this compound out in good yield, okay? By filtration. So this is a pretty straightforward step. Dump, stir, filter, and you've got your product, okay? This work here Well, an elegant route requires chromatography for purifying this compound, chromatography for purifying this compound, and chromatography for purifying this compound. Over the 3 steps results in about 68% yield and 2.2 grams. Now, chromatography is a very solvent-intensive purification method. So ultimately, for our approach, because we avoid chromatography, we can use between 50 mils to half a liter for this process to generate 4.5 grams, and the total time needed is about 1 to 12 hours. For this other approach, the total solvent use is between 5 to 7 liters, including all the chromatography. So we're dropping this by 100 to 10 times the amount of solvent that's used simply to make this compound, and dropping the total time by a factor of 4 or more, depending on the route that we use. Okay, so ultimately, the green chemistry approach here is that this is a much less resource-intensive, time-intensive, and energy-intensive way to get at this compound to do a bunch of interesting things in terms of forming strained intermediates. So ultimately, this has been a platform for new discoveries. Okay? This greener approach to generate arines from relatively simple starting materials. In one step, we can generate this precursor, and then we generate the arine, and we're generating a whole bunch of new intermediates where we're functionalizing these by forming 2 new bonds in one step. Potentially, there's new opportunities to go from the discovery phase to the process phase, but there's a whole lot of effort that would have to go into that process here. And to go from the scale of this on, say, 1 mil of solvent to thousands of liters of solvent is a pretty dramatic advance as well. So I'm going to leave you with that little story about our own research and how it fits into a green context. I'd be happy to answer any questions, and thank you all for your attention.